So today I want to explain a little bit more about module categories and in particular what it means to be a module over vector bundles on a stack. And the intention is that this is the last kind of general lecture in this direction, and we return to kind of nuts and bolts of Archipov Bezrukavnikov next lecture. And so if this seems like we're just doing general nonsense, please don't despair. I just want to explain a few complements to last time. So there's a general principle which some people call A modules are A modules, and I'll explain a little bit more what that means in a second. That's very useful, and I just want to explain it. It's not kind of directly useful for anything we're doing. I mean, it's behind the scenes of what we're doing today, but I just think it's a very useful general principle to keep in mind. Okay. So last time we saw that, I just want to recall. So let me give it just a tiny bit of motivation. So when we learn representation theory, we first are told a representation is an A module, or it's a homomorphism from A to some endomorphism ring of something. And our first impression, or at least my impression, is that these things are kind of out there and we try to get control of them. And then we prove a useful lemma, which is something like the regular representation generates all representations. And so what started out as a question of kind of things out there becomes a question of internal things. So we can study the regular representation and for example, for a finite group or something, we know that we can find all irreducibles within the regular representation. And so the question becomes an internal one. And the same thing occurs for module categories for over monodal categories, and that's this slogan, A modules are A modules. So we have, last time I just gave this example where we consider the representations of SL2C as a tensor category. And we had this theorem that A modules M, which are semi-simple and finite, i.e. finitely many objects, as so abelian as categories, and over A. So these categories up to equivalence are in bijection with finite subgroups. SL2C, and these are in turn in bijection with ADE Dinkin diagrams. And we had a number of very interesting questions. So one of them is, how the hell would you guess such a thing? Another interesting question was Emily's question, where she noticed that the classification, so if we have H inside SL2C, a finite subgroup, we have a homomorphism from rep SL2C, we have a tensor functor to rep H. And it turns out that all module categories for SL2C are of this form. And Emily observed that this here is a tensor category. And so we get the kind of module categories are tensor categories for free. And how general is this? And Anthony observed that one level down, this is the statement that they're kind of all left ideals are two-sided ideals, as would happen in the commutative ring. Okay, so this was last time. And now I want to just explain this philosophy. So if we have a monoidal category, so now we're just talking very generally again. We have the notion of an algebra is an object with a unit and a multiplication. Oops. So this means the unit of the monoidal category. And we have a multiplication such that the usual, such that blah. Okay, just such that the axioms for an algebra are satisfied. And then we can consider, inside this monoidal category, we can consider modules over this algebra. So we can consider mod A, which is right A modules. So this is M, an object of A, plus an action map such that module, right module axioms hold. Okay. And the important observation, or one important observation, is that this is a left. So this is a category. It's a category. And it's also a left A module. So given M a module, and X in A, then X tensor M is a module via identity of X tensor, the action map on M. Okay. So this gives us a process of going from algebras A in the monoidal category. Of course, I'm abusing notation here. An algebra is not just an object, it's an object together with a unit and a multiplication, satisfying blah. So this gives us a way of going from algebras in a monoidal category to A modules. And the meta theorem is that A modules are A modules. algebra in A. Okay. And for a precise version of this, so the annoying thing about this meta theorem is that it's not always true. But if you would like to see an example where this is true, there's this beautiful paper of Ostrich. This is a theorem for semi-simple rigid A, C, the Ostrich paper in the notes. Okay, so on the website of the course, there's some notes. And so the paper of Ostrich is called Module Categories, Weak Hopf Algebras and Modular Invariants. It's an absolutely beautiful paper to read about these things. Ostrich has this peculiar ability to give you just the right amount of detail. So he never seems to rave on too much, but everything that he says is necessary. Okay, so just to repeat, the kind of slogan is that we started off with this external search for modules over our monodal category, and one can turn this into an internal search for algebras within our monodal category. So if there's any questions, let me know. Just to recap, we're studying right modules over A, and this is a left module over script A, over curly A.
I'm confused. Why is M tensor A instead of A tensor M in the action?
Okay, that's we're studying right A modules.
But the action is okay. I understand.
And this is a little bit, so there's this whole philosophy about kind of doing something in a monodal category, like doing algebraic geometry in a monodal category. So we're used to, for example, studying algebras over a field, K, but various people have gotten quite a lot of mileage out of, for example, doing algebraic geometry in slightly more complicated categories. Slightly more complicated tensor categories. So for example, if you just look at super vector spaces, then you get the world of supergeometry. So I just want to explain without proof something. So this meta theorem, even in this case in Ostrich's paper, is not so easy to get. But once you have it, it makes certain classification problems very easy. And an example of that is the following. So what are module categories for finite groups? So we have G, a finite group. And K, an algebraically closed field, such that Kg is semi-simple. And of course, given any subgroup H inside G, just as in the SL2 example, we have a tensor functor the tensor functor of restriction. So this gives us a rep G module. So rep H is a rep G module. But a basic question is, are these all? And now an exercise that I would recommend doing to get used to this So in order to understand the answer to this question, we need to understand algebras inside rep G, i.e. we need to understand algebras with an additional G action. And if our category is semi-simple, it's easy to see that this algebra should be semi-simple. So we're looking at kind of semi-simple algebras with G action. And you can ask, what does this particular module category correspond to? And the answer is, so functions on G mod H is an algebra in rep G. And modules over this algebra so right modules inside this tensor category rep G over G mod H is equivalent to rep H. Okay. I have to admit that I am not particularly good at doing this exercise. So if you have a nice way of seeing this that doesn't involve too much work, I would love to hear it. This is definitely not something that I've digested particularly well. So in Ostrich's paper, he has the following theorem. So indecomposable module categories. Up to isomorphism are in bijection with basically, so subgroups with source. So H subgroups in G plus a 2 cocycle omega in H2 of HK star up to G conjugacy. And the association associates H omega to, so omega corresponds to a central extension K star H tilde H, a central extension. And this corresponds to rep 1 of H tilde, where this is reps of H tilde on which K star acts via identity character. And just some remarks / questions. The first remark is that the proof is surprisingly easy once one has the meta theorem. That A modules are A modules. i.e. it's reasonably easy to see that semi-simple G algebras in rep G correspond to this data. Two that I thought was interesting is that the objects on the left-hand side are not always tensor categories. Okay, so the analog of, so Emily's observation from last time is really pointing out that something special happens for SL2 that doesn't happen for a general finite group. Three, this is maybe a question for Professor Henderson. Is it easy to see that for SL2 these, is there a general reason? Perhaps this is a bad question. 0, 4. Why not? So I managed to convince myself that these classes are 0 for Z mod PZ for the cyclic subgroups of SL2. I have no idea why they're 0 for other ones. But I'm not sure if there's a general reason or if this is just an accident. And the last question, which is possibly for Professor Cliff, is so in the Stacks language, rep H as a rep G module corresponds to point mod H mapping to point mod G. And if that makes no sense, then hopefully it will make more sense after today and after next week. But I guess one is tempted to interpret these classes. So can one interpret? Okay, so the ones where this is a tensor category are the ones where you just literally have this category here is your module category. And one is tempted to say that these two co-circles are exactly classifying ways of twisting this category here. And maybe that's totally obvious to some people in the audience. I have no idea. Okay, so now we go to linear. So now we go to this. Basically, I want to try to summarize the relevant points of this short note of Gates' degree called the notion of a category over an algebraic stack. So I'll leave that for 10 more seconds. You're well aware of this by now, but I will explode in fury if anybody asks a question. So don't do it. The notion of a category . So this is, the reference is Gatesbury's short unpublished note. With this title. And maybe it's just to stay motivated, I'll just remember the motivation is that we suspect / hope that we have this coherent we want to establish a relation between this, so this is the coherent side, and the antispherical, so this is the constructible side. But then the equivalence is built up via establishing linearity over first point mod G check, then G check mod Lie algebra mod G check, and finally N tilde mod G check. Okay, and so we would like to know what it means for a category to be linear over a quotient stack of this form. What does this mean? And so this language of being linear over a stack will be very useful. I still find it a little bit tough to digest. Yeah, I guess it's a very important language. I think it takes some time to get used to, so don't be too concerned if it takes some time to make sense. So the setting throughout is C. So at the start of this note, Gatesbury says the purpose of this note is to explain the intuitively clear and probably well understood notion of what it means for an abelian category to be linear over a stack. And the paper is something like 11 pages. It's not particularly long. And then he says the much more subtle notion of a triangulated category or homotopy category being linear over a stack is the subject of a future work. And this future work appeared 10 years later and is about 100 and something pages long. And it has in the title, it has the notion of one affineness. So my understanding is that we can essentially ignore this complexity present in the second paper. And that's what Rome intends to do. So basically, this is a very complicated way of saying that throughout we're just dealing with abelian categories. And we impose a small size constraint on our abelian category. So we assume that C is abelian over K, over a field K. And we assume that C has inductive limits. Okay, so finite dimensional vector spaces would not be okay. Vector spaces would be okay. Coherent sheaves would not be okay. Quasi-coherent sheaves would be okay. And now we let Y be a stack, is a stack. And for those that were at lunch yesterday, you now know what a stack is. And for those that weren't at lunch, you should have gone to lunch. So yeah, so Masood says, why can we restrict to abelian categories when ultimately B's theorem is about triangulated categories? That's an excellent question. Basically, the point is that the triangulated categories that we have in mind are derived categories of abelian categories. And so we'll first establish the linearity over the abelian category and then extend it in a rather simple way to linearity to the triangulated category being linear. So we ask ourselves the following question. So what does it mean So roughly speaking, we should be able to kind of talk about what is happening near points of Y. So we can imagine that in some sense, this category is living over Y. So this may not be for all of us an intuitively clear notion as Gatesbury claims. But there is one case where it really is, which is when Y is an affine scheme. So let's do that case first. So it is so it's spec A for some K algebra A. So here we want, here the notion of being linear over spec A, we want the notion just to be A linear. So C linear over Y should mean that C is A linear. So i.e. A acts functorially A acts on Hom spaces. So some people in category theory would say that C is enriched in A modules. And another way of saying this is that we have a map from A to the center of C. This is the center is equal to endomorphisms of the identity functor on C. And throughout this business, I think it's really important to keep examples in mind. So if X maps to spec A, then quasi-coherent sheaves on X is A linear. So we think about quasi-coherent sheaves as being linear over spec A. And the important claim is that if C is A linear, then quasi-coherent sheaves on spec A, quasi-coherent sheaves on Y, acts on C. Okay, so in other words, we have a tensor functor C. And just our example continued up here is that quasi-coherent sheaves on spec A acts on Q co of X via pullback and tensor. So now we can, for example, say, if we have some morphism, we can ask, is it non-zero at a particular point, for example, by taking the skyscraper sheaf at that point and tensoring with that. So now I want to, so this is the important claim. Maybe we'll. Is this claim also true for general Y? It will end up being true for general Y, but it'll take us some time to get there. So this will be one of the models for what it means for a category to be linear over Y will be mean by definition an action of quasi-coherent sheaves on C. Okay, so proof. So we want to define M tensor X for where M is a quasi-coherent sheaf on Y and X is an object of C. Now, if M is a number of copies of A, so remember that Y is spec A, then define to be just the same number of copies of X. In general, we can choose a presentation of M and define M tensor X to be the co-kernel of A to the I tensor X to A to the J tensor X, where the ijth matrix coefficient by the aij action on X. So this presentation is given by some matrix of elements of A, And in order to form this co-kernel, I need to multiply by elements of this matrix. But because of my alienist structure, I'm able to do so. And the exercise that this is independent of presentation. And this gives us our action. And it's worthwhile in this particular case, just thinking, imagine that we have an action of quasi-coherent sheaves. Can we recover our A action? So we can also go back. So if we have an action of quasi-coherent sheaves on Y on M, we can cook out of this an A action, a linear structure, simply by noting that for all M in M, certainly the unit of quasi-coherent sheaves on Y acting on M is canonically isomorphic to M. But this is A. So the unit in quasi-coherent sheaves on an affine scheme is simply the trivial rank 1 vector bundle, which is the same thing as A. And so we get a map from A to the endomorphisms of 1/10 M, which is the endomorphisms of M. And this gives us a map from A to the center of C. And this is a kind of a toy example of passing between actions of vector bundles on Y and actions of quasi-coherent sheaves on Y. And for certain constructions, it's really important to have an action of quasi-coherent sheaves rather than just coherent sheaves or something like that. And the reason that's it's in order to have actions of quasi-coherent sheaves that we need some kind of inductive limits. How are we going for time? Okay. So now I want to briefly go over pullback. If there's no further questions here. There's one thing in the chat. Ah, that was the old question. So pullback. So imagine that I have a morphism of affine schemes. So we kind of want base change. So we have C that lives over S, which is spec of A. And then we have S prime, which is spec of A prime, and we have C prime that lives over here, and we have a morphism of affine schemes, which corresponds to a map like this in the other direction. And we, given C, we define the pullback as follows. So the objects are simply the objects of C. But they're equipped with an additional action of A. So if we take an object C, I was calling it before, apologies, M.
An additional action of A prime.
An additional action of A prime. So we have a map from A prime to end of M. And now we have, so M is an object of C. And so it has an A action. But we also have the map here, and this should commute. And morphisms are what you think. So they're morphisms are C morphisms compatible with the A prime action. And the exercise that I got horribly confused on, but Emily solved. For some reason, I thought this thing wasn't abelian, but exercise C prime is abelian. And just an example before we take a cup of tea break. If C is quasi-coherent sheaves on S, it's the same thing as A modules, then this base change is A modules with an additional A prime action. Extending the A action. But it's the kind of silly thing to say, you know, an A module with an additional A prime action. Extending the A action is just an A prime module. Which is quasi-coherent sheaves on S prime. Okay, and if I move this down to here, now we have functors from which we denote pull back and push forward, F lower star is just forget the additional A prime action. And F upper star sends an object M to. We've just seen that it makes sense to tensor with an A module. An A prime is an A module. And these are form an adjoint pair. Okay.
What's an example of an interesting alinear abelian category?
Equivariant cohomology of something, I guess.
Oh, what do you mean?
Like, I don't know, for me, things that, well, yeah, maybe this is not abelian, but somehow like the equivariant derived category is very naturally linear over the equivariant cohomology of a point. And that perspective is very useful.
Yeah, I don't think it's abelian though.
I agree. Another very, so a kind of causal dual example, which is abelian, is if you look at monodromic sheaves on something. So every object has a monodromy endomorphism. So this gives you, it's linear over something like functions on a torus.
Hmm.
And this example will be very important for us, I guess.
I guess I could just take perverse sheaves on something and see what that gives me. But then I'd probably just get base change of the sheaf coefficient.
So for example, if you look at perverse sheaves like on flag varieties, and this is linear over the center, which is the cohomology ring of the flag variety.
You're taking like these constructible perverse sheaves for this be constructible, not arbitrary perverse sheaves.
Correct. So I just wanted to give a brief review of descent, and as I said, this will be reasonably fast, and I assume that it's familiar to most of you, or to some of you. So in some sense, it's just a pointer of where to look to get more familiar with this notion. So descent is the basic concept that we can construct an object by constructing it locally. So giving some fancy complicated thing Z on X, where X is something like a space or a stack, is the same thing as giving the pieces of Z plus how to glue them together. And this is a kind of very familiar notion to mathematicians for a very long time, but Grothendieck's kind of, one of his extraordinary insights is that this notion of what it means to cover X can be interpreted extremely generally. So the origin of this idea was the notion that we could see, so if we have X, that we could see Y, where this is some covering space. So there was an observation of Sayre, which is that finite covers become a kind of not locally trivial in the Zariski topology, but if you allow yourself a sufficiently general notion of cover, then they become trivial. And so when we start off thinking about a cover as being something like some open sets that intersect in some way, and Grothendieck and Sayre explained to us that we should think more generally about, for example, a covering space as being something like an open cover of our variety. And the interesting case here is that the fiber product becomes a product of Y and the Galois group. And so in some sense, when we intersect open sets covering a space, we expect the intersections to be smaller. But in this particular case, we intersect two open sets and we get something that's bigger. And then Grothendieck taught us that that X going to X mod G is for G linear algebraic. Is what we should think of being a flat cover. So where this is a stack, this is the quotient stack. And if you haven't thought about these ideas, it's very important to think about them in some detail. So I just want to, what's the kind of silliest example of descent? So if we have an open cover of a space, then to give a function on that space is just the same thing as to give functions on the open cover such that some truth value is satisfied, namely that the values of these functions on intersections, so uij is ui intersect uj, agree. So now we only have a condition coming from intersections of two open sets. And of course, as we're all familiar with, when we go to sheaves, the notion of equality is replaced by a morphism of sheaves. And we have to require an additional, so now this is a morphism, so it's a morphism in a category, and we can ask whether morphisms in categories are equal. And so we get the condition, we get the gluing data for a sheaf, which is a collection of morphisms associated to every pairwise intersection of open sets. And there's one condition, namely the commutativity of this diagram. And descent for sheaves is the statement that to give a sheaf on X is the same thing as giving sheaves on the UI together with this gluing data. And my personal experience with descent is that it's generally a pain in the neck to check these things. So we can do the same thing with categories. So we imagine a sheaf of categories on a space. So now when we restrict, so this is what people call a stack. So I mean a stack in the very general term of a sheaf of categories, so stacks. So we're given, so giving a sheaf of categories on a space is the same thing as giving a sheaf of categories on an open cover. And now for a pairwise intersection of open subsets, we would like an equivalence of categories. For a triple intersection, we would like this composition of functors to be isomorphic to this composition. So we would like a morphism of functors. And so now we get these bijks, which compare the alpha jks. So we get over here. And now this becomes our condition, our gluing condition. So this is descent for functions. This is descent for sheaves. This is descent for stacks. Or descent for sheaves of categories. Okay. And just to tie into last week, I want to remind you that you can also interpret this. So you can kind of ask, where do these coherencies come from? And again, they come from a topological space called the nerve of the covering. So again, for simplicity, we're thinking that we have a cover in a classical sense. And now we associate to this a simplicial complex whose vertices are the parameterize our open sets. And we have an n simplex if the corresponding intersection of open subsets is non-zero. So this encodes in a very rough way the combinatorics of the intersections of our open sets. And here's a kind of classical example. So we take this cover of the circle by open subsets. So here's my first open subset, my second one, my third one. They all intersect, and so I get this simplex as my nerve. So this is called the nerve. And again, so last week we talked about how coherences for actions and monoidal categories comes from a cell decomposition of BG, and exactly the same thing happens here. So if I want to give a function on this space, it's enough to give a function here, here, and here, such that the pairwise intersections overlap. So that says that I should have a function here, a function here, a function here, and the only conditions come from one cells. So I can ignore this two cell. If I was giving a sheaf, I would need to give a sheaf here, a sheaf here, a sheaf here, an isomorphism here and here and here, and it should satisfy a condition here. And so the 0, 1, and 2 cells play a role. And in a category, the 0, 1, 2, and 3 cells play a role. Okay. So this is a way of giving a generator of relations description of what it means to give a sheaf of categories on a space. And just to, so for example, up here we had this funny commutativity that we needed to check, which I guess you could attack combinatorially, but another way of seeing it is that this commutativity up here comes from the 3 cell in this simplex. So roughly speaking, it's something like going should be the same thing as going anyway, I won't get this right, but so Masood says, so there's 2 good references for algebraic stacks and descent. So this is the general principle of descent. Okay. Is everybody okay with this, or is there any dissent? Okay, so now back to where we're up to. So the key lemma is that if S prime to S is a flat cover, so that means that this is a surjective flat map. Then to give then descent holds, then i.e. To give so C is equivalent to the so it's kind of descent data. C is equivalent to the category. So this is a flat cover of affine schemes. So C is equivalent to the category of satisfying descent. And moreover, any such category descends, any descends to S. And what this tells us is that now we can make an abstract definition for any stack. So so Y should be an algebraic stack. In the faithfully flat sense. So that means open cover means flat cover, and an affine diagonal. And the key property that we'll use here is that any map from spec A to Y is affine. And now I want to recall Emily's discussion from the IFS talk. So I'll just wait a little bit and then move slides. So what is a quasi-coherent sheaf? So I first want to recall what a quasi-coherent sheaf is on a stack. And then I will say the same principle allows us to define what a quasi-coherent sheaf is on an algebraic, sorry, what a sheaf of categories is on an algebraic stack. So what is a quasi-coherent sheaf? On Y. And the way to think about it is to pretend we have a sheaf, so a quasi-coherent sheaf on Y, but all we ever see is F upper star of this mythical creature for F a map from an affine scheme. And then we axiomatize what this would mean for F upper star of the mythical creature, i.e. For all maps F from spec A into Y, we're given F spec A inside quasi-coherent sheaves on spec A. And B, if we have a map, so write scheme aff Y for affine schemes over Y. So for any map from S prime to S, so we have, so S prime and S are affine schemes over Y. We want an isomorphism between what you kind of think is that we have an isomorphism from G upper star of F upper star of the mythical creature to G of F upper star of the mythical creature, but all we're allowed to say is that this is G upper star of F associated to S, and this is the mythical creature associated to S prime. And then plus a triple compatibility. So now we do the same thing for what it means to be to give. So there's a question. So for those who are not lunched together, in the faithfully flat sense means we're considering the site with the faithfully flat topology. That's exactly right. So in order for, this is in Grothendieck's universe, we need to say what it means for something to cover something. And we mean that this is a covering in the faithfully flat topology. And why is it important that F is affine? It is not. Roughly speaking, we're hang on a second, Peter. Yeah, so it's not important that our map is affine, but it's a little bit like affines are a basis of the topology. So Peter says faithfully flat equals FPPF or FPQC. That is, yeah, so you're right. So this is, I mean, so two people were complaining that I'm not allowed to write S like this, that it really depends on the map to our stack. And so either I can decorate this, or I can say that these are stacks over Y. So this index doesn't mean S as a scheme, it means S as a scheme over Y. So I might ignore Peter's question about FPPF or FPQC, because it is of a level of detail which is beyond the current discussion, but we can discuss after. So I should say that if this seems a bit like, I don't know, I always have the impression that this is some enormous amount of data that I'm never going to get a hold of. And in some sense that's true, but in some sense I think you should think about this in the kind of language of like the holistic and the generated relations. So actually, if we want to give a coherent sheaf on a stack, we would probably just take some small cover and write out these compatibility conditions explicitly. But it's also very useful to have this holistic point of view in mind. So we define. A sheaf of categories to be an assignment which does the following. So to any affine scheme over Y, we associate an abelian category satisfying the assumptions, which is linear. So this should be over S. And again, I'm using the same abusive notation. This is really a scheme over Y, not just a scheme. It's really important what that particular map to Y is. For each S prime to S, so this is a morphism in affine schemes over Y. We have an S linear functor. F upper star from inducing an equivalence if we base change CS. and and 3 we have for, if we have S double prime going to S star. So this before, this was the source of the triple compatibility for quasi-coherent sheaves, but now this will be a morphism which will then satisfy a higher compatibility. So for this in scheme YF, we have an isomorphism. This FG. Such that a three-way compatibility holds. Okay, and just again the remark that this is a holistic definition, and if we wanted to give a generators of relations definition, we could. Single prime. Sorry. Thanks, Josh. And now the kind of most basic example is S, if we take Y to be a point, and S mapping to quasi-coherent sheaves on S is a sheaf of categories on a point. And the exercise is to define the, so given define the kind of global sections of this sheaf of categories and show that it is a Y module. So vect Y is the category of vector bundles. Is on Y. And now the main theorem, which is, so the main theorem that I won't go into, I don't think much, I won't go into the proof of it. It'll be very useful for us, is that so we have some mild technical assumptions on Y. So these are just directly from Gatesbury's paper. So Y should be locally Noetherian. Plus every quasi-coherent sheaf is a limit of coherent sheaves. Okay, so this will be true in any setting that I've ever considered. And the second one, I think it's something like a kind of enough ample bundles assumption. So it's the statement that every coherent sheaf is a quotient of a vector bundle. So this is satisfied if there's enough ample bundles. And I think it's basically saying, what is coherent sheaf here? Doesn't this just mean its value on affine schemes is coherent? Emily, does that sound crazy?
I think Peter might be right that you might have to be careful, but I'm not sure.
Why might I need to be careful?
I have no idea if you need to be careful. I don't know what the definition will be.
I would just say that its values on affine scheme is, on an affine scheme is coherent.
Yeah, maybe it's fine because you're never pushing forward, right?
Yeah.
You're pulling back.
We're just pulling back, and pulling back preserves coherence.
Yeah.
So modulo some subtlety, that's what I mean by coherent. Okay, so the theorem is the following. And if anybody can see why this is saying something other than enough ample bundles, that would be very interesting. So the theorem is the following. So I interpret this as saying that something that I'll never construct. So the things that I've been defining up here seem to be pretty difficult to get your hands on objects. They're pretty kind of holistic things, whereas the things on the other side of this equivalence will be reasonably concrete. So the statement is that giving so the data of a sheaf of categories over Y. So under these assumptions, on Y, the data of a sheaf of categories over Y is the same as giving a vector Y module. So a module over vector bundles on a stack Y is exactly the same thing as giving a sheaf of categories over Y. And this is a very useful statement for us, because basically we want to construct things on the left-hand side, and things on the right-hand side are the things that will come to us. So if we're given a sheaf of categories, the correspondence over here is this global sections. So you can think about this as objects that satisfy descent inside here. So the key example is that, so if G is linear algebraic, a sheaf of categories on point mod G is the same thing as a rep G, as a vect. So vector bundles on point mod G are the same thing as finite dimensional representations of G module. And if you want a slogan, I might try and explain this correspondence in a little bit more detail after. So maybe the following example is useful.
So Geordie.
Yes.
So what we should remember is that if one can construct, I just want to see if I got this right. If one can construct coherent sheaves from vector bundles, then module categories over quasi-coherent sheaves are the same as module categories over vector bundles. Is that sort of the right way to remember?
So if you have an action of G-equivariant vector bundles, that's the same thing as giving a sheaf on your stack. So
yeah, no,
like,
I'm talking about the general theorem.
Mm-hmm.
So the left-hand side is just modules over quasi-coherent of Y, right? By definition.
No.
Oh, it's
the
not
left-hand side. No, the left-hand side is this association of all of these different module categories to affine schemes mapping to Y.
And that's not the same as module categories over quasi-coherent.
Quasi-coherent sheaves. No, so that's closer to the right-hand side, because we can do basically the thing that I explained at the very beginning to upgrade the action of vector bundles to the action of quasi-coherent sheaves.
Okay.
So there's an intermediate here, which is QCO Y modules. And these are equivalent. And this is like a kind of global version of the start of the lecture. So moving from an A linear structure to an action of A modules. And then the slightly more interesting thing is how to go from here to here. Namely, given any affine scheme mapping to Y, how do you produce a sheaf of categories on your affine scheme?
So my impression then was wrong, because I thought that this bottom right map, where this is global version, this is where you use that you can construct all vector bundles from coherent sheaves, right? And that red map, I thought that's abstract nonsense. Is that not the case?
It's abstract nonsense, yes. It's abstract nonsense, yeah.
Okay.
So is this what it means for Y to be one affine? Like that the category is determined by its global sections?
Exactly. So this is what, so in Gatesbury's long paper, he asks, when is this true in a more general setting? So this is kind of, as Emily says, this is category is determined by its global sections. And this is what people call one affineness. And the question of when this is true in a more general context is very subtle and explored in Gatesbury's paper.
And Geordie, can we look at this condition 2, the coherent sheaves can be obtained from vector bundles? So I don't remember what having enough ample bundles means. So can you just give us some examples of when this holds and when this doesn't hold?
So, for example, on a projective variety, given any coherent sheaf, you can, if you tensor it with O of M for M big enough, then it's generated by global sections, which tells you that it's a quotient of a number of copies of the trivial bundle. And now you can untwist to see that any coherent sheaf is a quotient of a vector bundle. And having enough bundles is basically, having enough ample bundles is basically this condition that you can twist enough to get things generated by global sections. So there's a fair few questions. So So Tony says there are affine schemes X for which O of X is not coherent, but the structure sheaf always pulls back to the structure sheaf.
So this comment is a complaint about the definition of coherent as like pull back to all affines is coherent, because then O would not necessarily be coherent.
But isn't that the complaint about whether the structure sheaf is coherent rather than whether this is a good definition?
I guess what I'm saying is that this definition doesn't recover the usual definition. Like if your stack was just a scheme.
But this is Noetherian, right? Locally, does that help?
No, so I think what I'm saying is because Y is Noetherian, OY should be coherent. But if your definition is like when you pull back to all affines, it's still coherent, then it violates that part.
I'm still missing something, but anyway. Yeah, I think I'm missing something in what Tony's saying, but
I'm just saying that like asking for the pullback to all affines to be coherent is too strong of a condition, I think, because you could take your stack to be like spec K, and you could find some affine scheme mapping to it for which the pullback is not coherent.
Yeah, I understand Tony's question. I think you need I think you need to require the map to be like a dial or something.
this would be too strong, but yeah, we need to require something on our map.
Yes. Otherwise,
okay.
You can't recover the traditional coherent sheaf.
Okay, so this is a fantastic point.
Yeah. So at least so that thing should also be like Noetherian or something.
The test scheme.
Yeah, the testing sheaf should also be Noetherian.
Mm-hmm. So so the questions keep on going. Can I think of a sheaf of categories on Y as a pre-stack over, but you don't need to land in groupoids? I would say yes. So a sheaf of categories is in particular a sheaf of categories in the sense that I'm talking about here is in addition it is a sheaf of categories in the kind of traditional sense, but we need more. Namely, we need that it's S linear. So I hope that makes sense. But yeah, the answer to your question is yes, but the sheaf of categories has additional constraints. And now Peter says, I'm guessing a non-quasi-projective variety doesn't satisfy the coherent sheaf is a quotient of a vector bundle condition. I think that's correct. I'm not sure. And do you want the test map to be a finite presentation? I think that's what we discussed before. Okay, so maybe I will continue in the, so yeah, we're getting close to the end. I'll just finish with the key example, and then I will do the brief remaining section of this next time. So the important example of a over point mod G. So I just want to give an example where you kind of see both sides of this equivalence and you see that something rather interesting is going on. So that's the following. So imagine that G acts on X. Now we can associate to this two pieces of data. So the first is the abelian category of quasi-coherent, G-equivariant quasi-coherent sheaves on X. And this is a rep G module. On the other hand, so this is the same thing as on the other hand, we can, to any S over K affine, we can associate quasi-coherent sheaves on X base changed to S, and this has an action of GS. So these are the S points of G. Okay. And so this side would be a sheaf of categories over point mod G. And this side is a rep G module. Okay, so. And these correspond under the above equivalence. Okay. So another way of saying this is that if I have quasi-coherent sheaves on X together with the action of G, it makes sense to take equivariant sheaves inside that category, namely kind of fixed points for the action of G, that recovers equivariant sheaves. And there's a formal way out of equivariant sheaves to recover quasi-coherent sheaves on X. So this is called, people call this equivariantization. De-equivariantization. Okay, so the passage from this is equivariantization and this is de-equivariantization. Okay. And I'll have a tiny bit more to say to this, say about this next week, and then we return to the main goal of Archipov Bezrukavnikov.
I just checked the definition of coherent sheaves on algebraic space. I guess it shouldn't be that different. So it depends on the topology. So it depend on the topology you are choosing on the site, and the test map should satisfy that topology. For example, if you use FPPF, then the test map should be finitely presented.
Mm-hmm. So that comes back to Peter's other technical question.
Yes. And yeah, so this will also solve the notarian question.
Yes.
What happens if you add the stack condition, like to my interpretation of a sheaf of categories?
So I don't think I understand the question yet.
Like I'm expecting a sheaf of categories to be a pre-stack over affine schemes over Y.
Mm-hmm.
So what if you add the additional requirement that that this is a stack, not just a pre-stack?
Yeah, I think the point is, I mean, you know, I'm not an expert, but there are many, many different sheaves of categories on spaces. So for example, things like sheaves of, like perverse sheaves, for example, form a stack on top of, you know, something like complex algebraic varieties or, so there's many stacks, but we're imposing that locally it's S-linear. So it kind of locally has a coherent sheaf flavor. And so I would say that what you're thinking of defining would be a much, much larger class of stacks than we're considering here. And maybe it's confusing that I'm saying stacks in two different senses. So just you're defining a general sheaf of categories, and we're looking at sheaves of categories that are locally S-linear, where
okay,
does that?
thanks. Yeah, I mean, I think that could, yeah.
But also so Tailan was asking if we can consider this as a pre-stack over that category, but you don't need to land in groupoids. But also we can consider a stack as a fiber category. So a category fibered on that category with fiber, like with groupoid fiber. So maybe in that, so maybe in this case, we don't need the fibers to be groupoids, and we need additional S-linear conditions on fiber. I don't know.
Exactly. Yeah, exactly.